Okay, great. Welcome back after the break. It's my pleasure to chair this next tutorial session, which will be given by Andreas Krause. Andreas is a professor of computer science at ETH Zurich, where he's heading the Learning and Adaptive Systems group. He also serves as the academic co-director of the Swiss Data Science Center and also is the chair of our recently founded new ETH AI Center. He received various awards. I'm just going to mention very few of them. He received the Deutscher Mustererkennungspreis, an NSF Career Award, the Occava Foundation Research Grant, but also various Test of Times awards for his research, for example, the ICML Test of Time Award 2020. His research on learning and adaptive systems has had impact in various domains. I think in particular, his work in the area of Gaussian processes, submodularity, but also safe reinforcement learning. Now, the latter is exactly the topic of today's tutorial. It's an extremely timely topic, I think, as it addresses a central challenge for robot learning in the real world. So if you have questions during the tutorial, just post them. I'll be collecting them for Andreas. And so now, without further ado, I'd like to welcome Andreas, and we're very much looking forward to your tutorial.
Oh, thanks a lot for the kind words. Let me share my screen. Can you see my slides?
Yes.
I hope so. Okay, so thanks a lot, Melanie, for the kind introduction. Thanks a lot to the organizers for inviting me to CoRL this year. Today, I'd like to give a tutorial on safe reinforcement learning. Just a few words. So this is based on a joint presentation with my former PhD student, Felix Berkenkamp. And so a lot of credit really goes to him. I'd also like to say that this is a super active research area with a lot of really smart people working on it, and with a number of researchers who've made seminal contributions to this area actually at this conference. So I'm very much looking forward to further exchange. It's also a very much emerging area with lots of exciting open questions. I've tried to break it down a little bit, also leave you with lots of references. Of course, in a short time, I'll not be able to cover all these aspects exhaustively, but hopefully we'll get enough to have some nice discussions. Okay, so let's get started. Given the audience, I probably don't have to say too much about what is reinforcement learning. So it's this abstraction of sequential decision-making under uncertainty that is an agent situated in some environment, which it can affect by carrying out some actions. And those might cause the environment to change its state and the agent to derive some reward from it. And of course, the trouble is that the agent doesn't know how the world works. So it needs to deliberate between exploration, so experimenting with different actions to learn about their consequences, as well as exploitation, using what it learned in order to do well. So this is a setting that's been extensively studied for several decades, both in machine learning, but also in control theory, so that approximate dynamic programming, adaptive control, and so on. So it has really a rich history. But we've all seen these amazing recent advances, and especially in the context of deep reinforcement learning. And you can't really talk about RL these days without just being impressed by the accomplishments that DeepMind had with their AlphaGo and AlphaZero agents in the game of Go. Now, these advances certainly created a desire and an appetite to use reinforcement learning to increasingly higher stakes real-world applications, such as autonomous driving, medical applications, aerial robotics, and other applications such as controlling our infrastructure. Now, I would argue, and I think many of you would probably agree, that there's quite a substantial gap between these situations where RL has been working super well in the past and a lot of the domains that we have on this slide here. So in particular, the settings where we really have seen a lot of advances in RL are situations where we have a perfect computational model of the world. Games are maybe the best example of this. Right, so we know precisely how the Go board looks once we and our opponent have taken our moves. And so that means that exploration is primarily a computational concern. It's a really difficult one. There's massive state spaces, and it's really impressive what can now be done given massive compute and advances in deep reinforcement learning. However, a lot of the applications that we've mentioned here don't have a perfect computational model of the world. So we might really have to work with situations where these learning agents make decisions in the real world. And as these stakes of these applications are quite high, we really want to make sure that these agents act in a safe manner. So when I talk about safe RL, I really mean this higher level questions of how can we think about agents that learn to act safely in a priori unknown environments. So I'd like to just briefly talk about a few applications that we've encountered in our research, and we'll talk about a number of others that are explored in the community going forward. So here's one that stimulated a lot of the research that I'm going to talk about in the second part of this tutorial, and that's a collaboration with Joel Burdick's research group at Caltech, who in turn works with clinical collaborators on the problem of spinal cord rehabilitation. So they work with spinal cord injured patients. And what was found is that by implanting these patients small electrode arrays that you can see on this X-ray image here and applying carefully chosen low levels of electrical stimulations, some of these subjects regain remarkable levels of bodily activity and control. And so now, of course, one challenge is that we don't have a perfect computational model of a patient, and patients react differently on this trade-off, to this treatment. So that means that any sort of learning algorithm that explores this large space of possible stimuli will really have to explore in the context of clinical trials. And I'll talk about some algorithms that later on actually have been used by Joel Burdick and his collaborators on the actual clinical setting. Now, given that this is the conference on robot learning, I'll also talk a little bit about robotics. So I'm not a roboticist myself, but I really like collaborating with roboticists. And this is a particular collaboration with Angela Schöllig, who is also the PhD co-supervisor of Felix. I'm also going to talk about one application. This is a large collaboration with the Paul Scherrer Institute. That's a large research facility in Switzerland. And we use ideas from SafeRL and Safe Bayesian optimization to tune their Swissfeld free electron laser. So this is a 700-meter long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second. And using this instrument, experimenters can image extremely fast processes, like molecules turning from one into the other in the context of a chemical reaction, which has lots of applications, say from drug design to materials discovery and many others. So what's the plan for this tutorial? So if we talk about SafeRL, we of course have to at least start talking a little bit about what we mean by safety, talk about safety specifications. Then we'll review very briefly about basically how to act safely in known environments, which of course is a big research topic on its own. But then we'll focus primarily on the challenges that arise when going to unknown environments. And a specific focus in the second part of this tutorial is going to be techniques of safe exploration. By the way, feel free to ask questions as they arise. So I'll do a short break in the middle where there's time to ask questions, but also feel free to interrupt before. Good. Okay, so let's start with saying what we actually mean by safety. So let's start with a cartoon. Suppose you have this quadcopter that's supposed to accomplish some task. Maybe go to the goal, and along the way it carries out some trajectory, some sequences of state actions, and we have to ask, is this trajectory safe, right? And presumably you don't want the robot to crash against the ground. You don't want to crash against the wall or some obstacle. And now one way to encoding this is using constraints. So you can imagine having some function G called safety function that takes a candidate trajectory tau and assesses how safe that resulting trajectory is. In principle, that could be a Boolean predicate. Oftentimes, it's really a real valued, without loss of generality, scalar function that we just indicate positive values with safe behaviors and negative values with unsafe behaviors. So in this concrete example, G of tau might just measure the closest proximity we ever have to any obstacle. Now, of course, specifying such safety constraints is highly application specific, as is the design of reward functions in reinforcement learning, and as such also already a very difficult topic. So what I just want to do is I want to point out that there's a rich literature really thinking about ways of how to encode using formal languages different kinds of safety specifications, and then maybe using techniques from formal verification in order to verify whether these assumptions actually have been met. So there's a lot more to say about how to specify safe behaviors, but I'm not going into much more detail but rather we'll see some concrete examples in later applications. Good. So if you go back to our RL loop, we now want to constrain it in a way such that the trajectories we encounter are safe to satisfy these constraints. The trouble, of course, is since our agent doesn't know how the world works, it can't just choose a trajectory, right? So it can only choose a policy which might carry some uncertainty about what sequence of trajectories we are actually going to visit. And that's, of course, where the key challenges really arise, that the effective constraints we have to deal with are not really known ahead of time to the agent. So it means that now we have to somehow take the safety specification of individual trajectories or behaviors and turn them into some objective that we can incorporate in optimization. And of course, there's also various different ways of doing so. So we might, for example, ask that no matter what, we want to make sure that all trajectories we can possibly encounter are safe, right? So thinking about the worst case realization of this safety function. And now in situations where the model is really quite well specified, maybe you have some bounded disturbances and so on, one can use ideas from formal verification, robust control, and so on in order to guarantee really worst case safe behavior. Now, in a typical setting of reinforcement learning, where there's a lot of uncertainty about the consequences of actions, typically requiring trajectories that are safe even in the worst case is typically too much to ask and often leads to extremely conservative behavior. So if you want to go away from it, you have to somehow talk about uncertainty quantification now. And of course, a standard language to reason about this is probability. It means that now we have a distribution over possible trajectories. And I'd like to point out that there's different notions of uncertainty that can factor in here. So even for deterministic systems, you might just have epistemic uncertainty about, say, the unknown dynamics of the system. But of course, we might also face explicit stochastic environments or use stochastic policies. So in the end, we're going to have now a random variable that encodes basically the distribution over our safety function value for these different random trajectories for any candidate policy. Okay, so which might have, say, a distribution that looks like this. And we now need to quantify it somehow. One way to do it, of course, is to look at the expectation and ask that the system is safe in expectation. So require that the mean of this distribution, say, is above 0. Now, of course, that can lead to some undesirable consequences. So you can have situations, especially if this distribution over our random variable G is multimodal, you can have situations that you're safe on average, but most trajectories are actually unsafe. Now, of course, one can think about other ways of taking this distribution over these possible safety values and quantifying the risk in a certain way. One way to do so is to, for example, require that most trajectories are safe, right? To bound the failure probability, which basically means that we're now going to put a constraint on a pessimistic estimate on this random variable G, or a lower confidence bound on this random variable G. We might, for example, say that we want the robot to crash at most 10% of the time, or probably have more stringent safety requirements. Okay, so this is now a way to sort of turn safety into a set of constraints. And now what we'll see later on in this tutorial is actually a range of techniques that basically operate using this notion of value at risk and use ideas from formal verification, robust optimization, where now we don't constrain the worst case over all possible trajectories, but only over all plausible ones that are sufficiently likely. Okay, so this is the value at risk. I also want to point out that, of course, there's a lot of other risk measures. So one popular one that's widely used is the conditional value at risk. It's the lower bound on the value at risk. It's the expected value conditioned on being in the tail. So the average over the tail of this random variable within this alpha F percentile of the values it can take. And that notion of risk has a lot of desirable computational properties. So one can, for example, under some circumstances, relate it to an expected notion of safety with a certain transformation applied to the returns. And this idea has been widely used in various different fields, mathematical finance, but also in robust reinforcement learning and so on. I'd also just like to point out, so there's actually 2 papers at NeurIPS coming up this year on looking at algorithms for doing really stochastic large-scale optimization with this criterion, really pushing the boundary of models that can be optimized with it. Good. So we've seen a bunch of different notions of safety. both in sort of the worst case and the stochastic setting. Of course, there's more than we can review here, right? But we've talked about some of the important ones. And of course, which one to pick depends on requirements of specific applications that we might face, but also, of course, any sort of knowledge or prior knowledge we might have about the system. Of course, the choice of these different notions of safety also has important algorithmic consequences in terms of our ability of solving the resulting approximate dynamic programming problems. So this leads us to this question, how to act safely in known models. What I mean by a known model is that we now actually have a model where all the uncertainty is well specified. So for example, a Markov decision process where we have given certain constraints, or maybe a deterministic system with certain sets of disturbances that we possibly can consider. And so now, depending on which notions of safety you consider, there's a whole range of different solution techniques. I just want to briefly mention a few. So one important one are constrained Markov decision processes. So here we typically talk about safety in expectation, that a safety function similar to the reward decomposes additively across different time steps. And this additive decomposition and linearity of expectation then allows to use similar techniques that can be applied in the unconstrained setting, for example, P-based solution techniques or other approximate dynamic programming formulations. Of course, robust control, looking at the worst case over a set of disturbances, is extensively studied, agent stability control, and so on. And there's a lot to say about these sort of methods. And of course, there's ideas in between. One can combine ideas from sort of worst case and stochastic optimization. For example, optimize the expected behavior with respect to a worst case MDP out of some set of possible MDPs. So that's related to distributionally robust optimization, which is a large research area, of course. And this field of how to act basically under safety constraints under a known model is still a very, very active research area with lots of exciting advances. So as we said, we want to focus on a setting that we don't have a known model of the environment. So it means we really want to think about agents that get deployed in the real world and sort of learn by acting, okay? And so that means that our poor agent now doesn't know about the consequences of the actions, can't simulate forward what might possibly happen. And of course, this is where the real challenges arise that I want to focus on in today's tutorial. So now the first question, of course, where do we even start? Literally, where do we start, right? What's even the first policy that we can deploy that nothing bad happens? And so it's pretty obvious that without any sort of prior assumptions, it's completely impossible to act safely, right? So this should be pretty clear. So the main question really is, what are different ways of infusing prior knowledge in coming up with the first feasible policy to solve sort of the feasibility problem? And I want to talk about some ideas that have been explored in the literature, besides sort of explicit construction of first principle models. And so one important area, of course, that's been quite widely studied is imitation learning. It's a large research area on its own, where prior knowledge comes in form of a human expert, say. Okay, so there's an expert that has in their head a safe policy, pi star, that would prescribe a safe action in any state, and we can query this expert for advice. Now, how does this work? So you would start maybe with some training data set of a bunch of different demonstrations, basically trajectories labeled by the human expert. And then given this data set, we can try to learn a parameterized policy, say parameterized with a neural network, and try to basically solve a supervised learning problem where we try to predict the expert's action for any given state. Now, of course, the key issue here is that we immediately leave the IID setting and there is a substantial domain shift. So while we are close to states where we have labels by the human expert, things are fine. As soon as we deviate from those states, the policy is going to do something crazy and the agent is going to not do well. So now, there's, of course, this is a classical problem in imitation learning, and there's ways to fix this, in particular by keeping the sort of collecting more and more data. And so techniques like data aggregation and policy aggregation. So I just want to talk briefly about data aggregation. Here, the idea is that instead of just solving the supervised learning problem once and deploying the resulting policy, what we're actually going to do is we're going to roll out the policy, but then ask our expert again to obtain new labels for the states that this policy visits. And then, of course, we're going to update the policy and iterate. And so now one can analyze this resulting algorithms using ideas from regret minimization and actually show that under some conditions, this is guaranteed to have low regret, to actually converge to a good policy. Now, so far in the basic setting, safety doesn't really appear. So here it means that when we roll out the policy, it might very well happen that bad states are being visited, right? And safety constraints are violated. And so there's quite a bit of really interesting recent work on thinking about safety in the context of imitation learning that I just want to point out. And so here, one basic idea that's been explored is to not just blindly apply the policy that's learned, but basically try to figure out when you can trust it. So for example, one can try to have a separate learning model that tries to predict whenever the learned policy is going to produce an action that's close to the expert's policy. Or one can also try to quantify the uncertainty in the prescribed action by the policy and then require, for example, only play the action when the policy is sufficiently confident about what the correct action is. So in sort of the cartoon picture here now, we follow our rolled out policy in red. At some point, we detect that we are doing something bad. So we're deviating from where we know what to do. And at that point, we relieve control to the human expert to collect more data. And then, of course, the hope is that eventually, as we collect enough data, the expert is asked as little as possible. Okay, but so that's different models that have been explored here. There's many interesting open questions in this context of safe imitation learning. So another idea that we've been recently exploring, that's a paper coming up at NeurIPS this year, is to use a different form of domain knowledge and infusing it using concepts of curriculum learning. So this is sort of inspired from how basically little kids learn without failing. So if you think about children learning how to ride a bicycle, they typically are given some help, right? So maybe the supervisor would hold them and try to make sure they don't fall or give them training wheels, etc. So the question is, can one sort of have training wheels for reinforcement learning algorithms? And here's sort of a little illustration of how one can think about this. Here, this is the illustrated in the lunar lander environment. So we want to learn this stylized spaceship on this planar surface on the moon. And so now this is not a very difficult RL problem, but it's difficult one to learn without crashing. So now what you could imagine is instrumenting a set of training environments before the policy actually gets deployed, where, for example, detect that the agent enters some bad states and apply some sort of intervention. So for example, as soon as the agent here leaves this particular funnel, it would be reset to a state that's close by. So that's one possible intervention. Of course, there's many possible interventions. And now one can think about sort of this meta problem on how to optimize over curricula of such possible interventions. And so now, in contrast, if you sort of start just solving the original MVP, it can solve the task quite well with lots of reward, but it would fail very, very often. And now by applying these different interventions, you avoid most of the failures. On the other hand, learning gets harder and also returns get smaller. And these depend on sort of these different interventions. And by optimizing of these curricula, you can basically get back the same performance without failing along the way. So this is sort of a different way of how one can think about infusing prior knowledge, where maybe at the training phase initially, one can sort of instrument the environment in different ways. Okay, so now we have some initial safe policy. The question is, how can we do better, right? So we have a feasible policy, but we want to find a good one, right? We want to optimize performance in some way or the other. Okay, and so now that's sort of the next question. And for the rest of the tutorial, we'll explore various different ways of how to do so. So I'll first briefly talk about some set of techniques that rely on certain types of prior knowledge, again, in order to basically allow the agent to use learning to deviate from the initial safe policy while ensuring that bad states are not visited. So let me just sort of illustrate this. So suppose we are sort of in a situation where we actually know and we can diagnose when bad things are about to happen. So here's sort of this cartoon illustration, right? You sort of see this quadcopter that's close to sort of crash against the wall. And now what we can try to do is we can try to think about sort of an architecture that we wrap some safety mechanism around the learner, right? So we have some sort of safety controller that then gets to take over before the agent crashes against the wall, and then relieves control to the learner again, as long as it's safe to do something. Okay, so this basically allows to use this initial safe policy, inject a bit of learning in different ways, but then sort of create this boundary, a shield, a filter around it in order to avoid bad things happening. So here one can sort of think about essentially a form of robust control where the learner is seen as some sort of disturbance has to be taken into account. And there's a range of really exciting work that explores various different facets of this concept that I'll not be able to review here in much detail. So there's ideas like shielding or safety filters that have been explored and are very effective for such settings. So this is a way of incorporating certain kinds of prior knowledge, not just when coming up with the initial policy, but also to sort of isolate learning in the context of the larger system to make sure that the effects of the learner are bounded and can't lead to disastrous consequences. So another interesting related concept that's been explored by Yisong Yu and his collaborators is, instead of using hard constraints on the allowed policies, is to use the idea of functional regularization. So instead of optimizing simply the performance, say, of a policy, you would also add some regularization term that inject certain types of control theoretic prior knowledge. So prefers certain policies that, for example, are smooth or satisfy certain stability properties and so on. And so here are some relevant papers on this line of work. And also there's some cool applications that Yisong and his collaborators have been looking at in the context of simulated car racing or controlling autonomous robotic cameras for optimizing news coverage in sports. So basically, these approaches are different ways of essentially using prior knowledge to sort of shield or bias the learned policy in some way or the other. But of course, you somehow need to have this kind of domain knowledge as a constraint. So now, of course, the natural question is, can you reduce this dependence on prior knowledge somehow? And in the following, we want to explore some ideas that go in this direction. So so here let me start to talk about one such approach, which is specific to expected safety as a criterion that we had talked about, say constrained Markov decision processes, for example, as we had talked about. Okay, so suppose again, we have our initial safe policy, theta B, our baseline policy that we can deploy, and we care about say optimizing its performance. So for sake of this presentation, I'll actually set the performance objective equal to the safety function. But of course, one can also separate these two objectives, and that's been studied in the literature as well. So safety basically requires that whatever policies we consider deploying on the real system, theta, we want to ensure that with high probability, the performance of this new policy is at least as good as the baseline policy, with some high probability that we get to specify ahead of time. So it's really a conditional expected safety. So expected safety criterion, but we want to bound the failure event where this happens. Okay, and so now what we would like to do is we want to avoid using prior knowledge, but one way to replace prior knowledge is prior data. So you can, for example, take a look at trajectories that are collected from this safe baseline policy. So for example, we can run this baseline policy to now get sort of a distribution of our possible trajectories. And now we can try to use this data in order to evaluate a new policy that we're considering. So this is an area called off-policy policy evaluation. It's also a super important, exciting subfield of reinforcement learning. So we want to ask what do these observed trajectories tell me about the performance of some different policy that we consider deploying? And there's a class of techniques that basically revolves around importance sampling and variance of this. So what we can do is we can, if we care about the expected performance with respect to a new policy, we can simulate according to our safe baseline policy and then apply some importance correction in order to get unbiased estimates of the original objectives. Okay, and now this importance correction, crucially, can be computed purely based on knowledge in the policy. So the probability of different actions that are being chosen under different states. So now this is sort of the most basic idea. There's much better ways of doing this. So a crucial concept to look at here is this notion of eligibility traces. Okay, so now using this, we can sort of try to ensure guaranteed improvements of our policies. So what we've discussed is how to obtain unbiased estimates of J of theta. But of course, there's going to be a potentially significant variance in these estimates. And so now a key question is, if we want to ensure that we improve with high probability, then we somehow need to estimate something beyond expectations. And what one can, at least in principle, do if there's, say, bounded values of our function g or j, then we can use concentration inequalities in order to obtain confidence estimates. And those basically allow to obtain statements of the kind that you can lower bound with high probability the expected performance or expected safety of some new policy as this importance corrected unbiased estimate minus some term that does depend on the number of samples that you've used. Okay, and so the overall setting would sort of look like we simulate forward these trajectories according to the baseline policy to get a training and a test set. You would maybe optimize over candidate policies in the training set, and then evaluate them in the test set, and then use policies only if you're confident that they're safe. Now, of course, there's many details to this. So these ideas have been studied quite a bit in the literature. So first, this basic idea of essentially constraining, so obtaining these policy estimates, but then also thinking about solution concepts. So how to now optimize policies under constraints that basically of the kind that we have described before. Okay, so this is basically the first part of what I wanted to cover. So we reviewed some of the basic safety definitions, both in the stochastic and the worst case setting. We identified as sort of a first challenge, this key issue of how to come up with a first safe policy, and then started to explore different ways of how we can now sort of integrate learning on top of this first safe policy in order by using either prior knowledge or using data from a baseline policy in order to improve performance. What we want to do in the second part of this tutorial is to explicitly look at this challenge of safe expiration. So maybe now is a good time to just take a few questions, and then we can continue with the second part.
Great, thank you, Andreas. There's also a first question in the Q&A. So how can you apply the curriculum intervention idea in an actual system where you can't do an intervention? So for example, an autonomous car versus the lander setup where you can.
Sure, so it's a great question, right? So basically, whether one can do these types of interventions very much depends on particular applications at hand, right? And that is something to be investigated in future work. So here we look at the basic concept in these simulations and do a bit of theory in this context here. Maybe one thing to point out, so this curriculum learning idea can already be very valuable in order to solve challenging constrained MDP problems, even to come up with feasible policies for constrained MDPs, and we demonstrate that in the paper.
Okay, great, thank you. Are there any other questions that people would like to post? For the moment, I don't see any. Okay, good.
I'm happy to continue, right? And we can feel free to interrupt me anytime. And of course, there's more time at the end. Good, so let's talk about safe exploration, right? So it means that we want to learn how to act in these unknown environments. We now have some sort of policy that is deployed on the actual robot. and now the actual system that we control, we collect some data, and from that we would update the policy. And of course, now the question is, how do you collect good data in order to find good policies? And so now to dive deeper into that, so there's different settings, of course, that are studied in reinforcement learning, both the model-free and the model-based setup. In the model-free setup, we consider some parametric family of models. What we would do is we basically try to solve this global optimization problem over the parameters of our policy in order to optimize the performance. And of course, in the model-based setup, the idea would be to, based on data, learn a model of the environment and then plan accordingly. So I want to, so the mechanism that we'll be exploring to encode safety here is to be explicit about the uncertainty, both in the objective and the constraints, and then use this uncertainty in order to ensure constraint satisfaction with high probability, effectively placing a bound on the value at risk. So I'll start illustrating this idea in the model-free setup, in particular in the context of safe Bayesian optimization. And then later on, we'll talk about the model-based setting. And so here, let me just, as a concrete motivating example, come back to this problem of how to tune the Swiss-Fell-free electron laser that I briefly talked about at the beginning of this tutorial. So this is a pretty complicated machine with a lot of literally moving parts. So the electron beam properties are shaped using a number of different magnets that can be controlled in real time. And the beam properties very subtly depend on essentially the configuration of these magnets, as well as additional environmental properties like temperature, humidity, and so on. So they basically need to be adapted continuously over time. And there's also often typical different application requirements in terms of beam properties that the policy need to adapt to. Now, there's also safety constraints. So if we're not careful, what can happen is that there can be beam losses that might cause damage to some of the magnets of this system. Of course, that would be super problematic if that were to happen. Of course, there are some safety mechanisms in place that will just shut off the machine, but you also don't want that to happen during live experiments. This experiment time is really expensive. So in order to detect possible constraint violations, so basically the corresponding safety specification is through beam loss monitors. So these are basically monitors placed throughout this device that actually measure whether there are beam losses and effectively allow you to monitor how close you get to violating any of the constraints. And so now basically we can sort of think about this problem as essentially a sequential decision problem where every round theta t, we inject some parameters on how to configure our magnets. Then we get a noisy measurement of the beam performance. That's our reward. At the same time, we get a noisy measurement of our constraints. Here in this case, reported by these beam loss monitors. And given those observations, we want to decide how to proceed, right? What next configuration to propose. Now, of course, the goal is to solve this constraint optimization problem where we want to maximize performance subject to these constraints. However, we want to ensure safety, not just at the end to find eventually a feasible solution, but we want to guarantee feasibility of all iterates. So every single experiment we carry out has to be safe with high probability. So basically, we have to solve an a constraint optimization problem with an unknown objective and unknown constraints that can only be accessed up to noisy zero order feedback, so noisy measurements. And we want to guarantee feasibility every step along the way. So in general, of course, this is a completely hopeless task. So we need to figure out when one can actually try to make progress with the setting. So here's sort of a cartoon picture to illustrate some of the concepts. So the x-axis is now the set of parameters. The y-axis is the performance, which for sake of simplicity is just set equal to the constraints. And so that means we want to maximize j of theta, basically, while ensuring that wherever we evaluate the function, we're above the safety threshold. Now, without any prior knowledge, even the first action could be unfeasible. So we make the same assumption as we've discussed in the first part of the tutorial, that we have some initial safe seed for exploration, so safe feasible initial policy, indicated by this cross here. And starting our exploration from there, of course, ideally, we'd like to find the global optimum. Now, it should be pretty clear that in general, this is not possible. So without any assumptions on the shape of these objectives, this is a hopeless task. So we'll have to make some sort of regularity assumptions, and I'll be more specific about those. But even under some sort of regularity or smoothness assumptions, we can't really hope to leave this red set here, which is the connected component of the feasible region that contains our safe seed, our starting point for exploration. And so the benchmark that we're going to compare to is the reachable optimum, which is the global optimum on this red set, or for high dimensional settings, we can really only hope to get to local optima on this red set. Okay, so now how do we encode prior assumptions on the objective and the constraints? So one way to encode prior knowledge is to take a Bayesian approach and basically view our objective and constraints through the lens of a probabilistic model. And that's exactly what's done in the field of Bayesian optimization. So we would treat the unknown objective as a random function drawn from some distribution over functions on which we can then condition to make predictions, not just with respect to the performance of experiments we haven't carried out, but also quantifying the uncertainty in the resulting prediction. And now this distribution can now be used in order to come up with a surrogate objective called an acquisition function, which allows to navigate the exploration-exploitation dilemma. And so there's a whole range of different acquisition functions that are used in Bayesian optimization, both in the unconstrained and the constrained setting that I can't review in detail here, but I want to explain some of the most important ideas. So first of all, you have to specify what kind of probabilistic model you're going to use. In the illustrations, we are going to use Gaussian processes. That's maybe the default choice in Bayesian optimization at the sweet spot between expressiveness in terms of applications, but also tractability, both computationally and mathematically. But in principle, many of the algorithms can also be used for other models like Bayesian neural network models and have been used in the literature. So as a Bayesian model, once we carry out experiments, we can condition on them to get a posterior distribution that contracts given more and more data, right? And now the smoothness of that resulting function or the regularity conditions are imposed through the covariance function of this Gaussian process, which basically expresses prior knowledge on the strength of correlation or covariance of the function response between pairs of inputs. So this tells us everything we need to know about smoothness of this resulting model. So how is the uncertainty useful? Here's sort of a key picture. So suppose we've carried out a bunch of experiments shown by those pluses here and calculated our posterior distribution with mode given by this black line and uncertainty given by these gray confidence bars. And suppose we are in the situation where with high probability, the true function lives within these gray confidence bounds. Then we can apply the following rationale. So we can look at the best lower bound, so maximizing the lower confidence bound of this model. And now if the model is well calibrated, so the true function is contained in these confidence bounds, the maximum must be somewhere within these green regions where the upper confidence bound exceeds the best lower bound. And that is often used as a justification for the famous optimism in the face of uncertainty principle in reinforcement learning, which just plays the point that maximizes the upper confidence bound. However, if safety is in place, maybe being too optimistic is also problematic. But of course, one can make use of the same picture to also reason about safety. So if this is our safety threshold, then of course we can now look at a pessimistic estimate, say of our constraint, given by the lower confidence bound, and say focus our exploration in this red subset of the domain where the pessimistic estimate exceeds the safety threshold. So it's a conservative inner approximation of the feasible region. Now, in order to realize those pictures, we need well-calibrated confidence bounds. And that alone is a very difficult topic. But it turns out for Gaussian processes in particular, there's some results that can be used in this context. So first of all, confidence bounds for GPs are simply mean plus a multiple times the standard deviation. These enumerate percentiles. But now, if you want to rely on these confidence bounds algorithmically, we need to make sure that they're calibrated in a way that they hold uniformly over all iterations of the algorithm and everywhere where the model uses them in order to make predictions. All right, so essentially that's sort of a massive multiple hypothesis testing problem that we have to correct for. It turns out one can indeed correct basically and scale these confidence bounds, even in sort of a frequentist setting where you don't even make a prior assumption, a Bayesian assumption about the unknown function. You have to scale the function such that the unknown objective sort of agrees with your prior, and that sort of agreement can be measured in terms of the complexity of the unknown function, evaluated according to the reproducing kernel Hilbert space norm of this unknown function with respect to the covariance function that Gaussian process uses. And then there's a second term that depends on the capacity, so that the admitted degrees of freedom of this Gaussian process model, which can be numerically accurately computed for any given kernel and can be analytically analyzed, both using ideas from submodular analysis. So there's quite some literature on this. I will not go into much more detail here. There's also some recent work that looks at, for example, adversarial perturbations and misspecification in these sort of settings. So what matters for us is that at least under some circumstances, we can really understand under which conditions we might be able to get such well-calibrated confidence bounds for GPs. And one way of using them is the safe opt algorithm. So it basically uses the Bayesian model for our objective and our constraints. So we want to make sure that wherever we evaluate, we're safe. So G of theta is above the threshold. So we're going to use our prior on J and G. And now we use them in order to come up with our safe sets, right? The conservative approximation in red, as well as the set of plausible maximizers. And now in principle, what we could do is we could just say, let's be optimistic, but constrain our choice to this red subset of the domain. The problem is that this strategy very quickly gets stuck in poor local optima. And the reason for this is that the set of plausible maximizers in green is typically contained in the strict interior of this red set and has no incentive to push the boundary to try to figure out different areas in our parameter space where we can achieve improved performance. So we also need to look at some notion of expanders, so indicated by those purple points. Intuitively, these are points close to the boundary where observations plausibly allow to infer that additional actions are safe. And now basically among those points that are relevant, plausibly optimal or expansive, we pick the ones that provide as much information as possible. And eventually we figure out that better solutions are actually found over here. Okay, so that's the safe opt algorithm. And under the kind of conditions described before, as long as the confidence intervals are well calibrated, one can guarantee both safety and completeness for the resulting algorithm. So guarantee that the algorithm will never make an unsafe decision. And one can even analyze sample complexity, so bounds the number of iterations it takes to get an epsilon optimal reachable point of this algorithm. Now, I'd like to say, if you ask really for global optimality on the safe set, then there's constants here that are exponential in the dimension, and that's impossible to avoid. However, if you're happy with locally optimal solutions within the safe set, then one can get away with polynomial dependencies. So there's work on this. So that's the first reference, and there's quite a number of other approaches that have been exploring related ideas in the literature. So here's the first demonstration of this that Felix did a few years back in Angela's lab on a simple quadcopter task. So this quadcopter here just flies from A to B. So we start with an LQR controller as our initial safe policy that's derived from the first principle model, which is chosen conservatively. So it gets there, but is not very efficient. And now what we do is we inject some controller gain parameters and use safe Bayesian optimization in order to tune them online in order to optimize performance under constraints. I'd like to point out that most of these parameter settings will immediately destabilize and crash the robot. So if you just play optimistic exploration, for example, then you're being too optimistic. So I'll just let this run for a little longer, and then we see a quick comparison, and then we'll move on. So this is, so you basically, the algorithm allows to sort of gradually enable less and less conservative behavior as more and more data is being collected. So as mentioned, here are some results on this spinal cord therapy application. So as I mentioned to you, so Joel and his collaborators, Yanon Sui, Zhang, and Yue, applied a variant of the safe opt algorithm called stage opt actually in the context of clinical trials, and they were able to actually find recommendations for stimuli that performed as well or even outperformed the best choices found by the physician. So I very much encourage you to take a look at their paper. So here some results on the Swiss free electron laser that I mentioned to you before. So here we use a variant of the algorithm that's designed to scale to much higher dimensions. So we address it here to a few tens of dimensions that we tune live using this algorithm by using randomly chosen subspaces and applying the algorithm on those randomly chosen subspaces. And there's a convergence analysis in our ICML paper describing this algorithm. And so here, the sort of experiment that we would do is we would take expert settings given by the physicists. We would adversarially detune them so that the laser has bad performance. And then we would use different algorithms in order to try to recover high-performing parameter settings under these safety constraints. And so in most cases, the algorithm is not only able to recover parameters as good as those by the human expert. Sometimes they even outperformed the parameter settings that were found by the expert, and also outperforms standard local search techniques that are used in this domain. Good. So this is some ideas on safe exploration in the model-free setting. And so one thing I'd like to point out that essentially all the work that I've described so far focused on the so-called episodic setting, where we're actually able to reset the learning agent safely to some starting state. So repeat the same experiment, and we sort of want to find settings that optimize performance while satisfying safety constraints. But of course, many really important challenges arise if you can't reset the agent and if you really have to plan ahead and have to worry about reachability. So in the last few minutes of this tutorial, I want to talk a bit about techniques of how to reason about ergodicity of the resulting behavior, reachability, and so on in the model-based setting. Okay, so now, as you said, we want to look at the model-based setting. That means that the data we get through exploration, we want to use to learn our model. And our safety, basically, again, we want to make use of uncertainty in that model that we want to learn. So you're going to learn probabilistic models. And we use the uncertainty in the model in order to ensure safe behavior, similar to what we had to describe just before. Okay, so how does this work? So we first have to start with certain modeling assumptions. So here we'll be thinking about nonlinear dynamical systems, where at any state ST we apply some action AT, and the model would basically prescribe the next state that we get to. What is often done in the literature is to assume prior knowledge in form of some first principles a priori model, and then learn disturbances or basically unmodeled behavior discrepancy between the first principle model and observations from data using an unknown model that is then learned. And the set of approaches that we'll focus on here now also use Gaussian process models for those resulting dynamics. And such Gaussian process dynamic models have a very rich history and have been extensively looked at and studied in the literature. So how would they look like? So now if again, in this one-dimensional cartoon, the x-axis is our state action pairs, and the y-axis is now the ST+1, so the consequences of our actions. We would have our unknown function as shown here. We have our a priori model given by this mean function of the Gaussian process, and then we have some uncertainty around it. Given data, our uncertainty contracts, and we gradually learn more and more accurate models. And as a consequence, as the uncertainty decreases, this reduced uncertainty will allow less and less conservative and higher performing behaviors. So I'd like to point out that there's a lot of really exciting work exploring such learning-based approaches, especially in the context of model predictive control. And so I only have limited time in this tutorial, so unfortunately I will not be able to present all this work, but here's references that I strongly encourage you to take a closer look at. I'll talk about some of these approaches going forward, but there's just so much exciting work that's really hard to portray in such a short tutorial. So first, I'd like to talk about some early work on using such learning-based model predictive control in the context of autonomous driving, just with a little bit of a motivating example. So here's first some work from Andreas Krause's group. So they use an outdoor robot. They use Gaussian processes to forward predict plausible dynamics. So initially, the model is quite unsure. So the robot has to drive very slowly to ensure safety with high probability going forward. And then as it collects more and more data, the model becomes increasingly confident about its prediction, hence enabling faster driving, right, and higher performing behavior. And so there's also some super exciting work in Melanie Zeilinger group using these ideas for autonomous racing. So some really cool papers to read in some more detail. So in the following, I want to talk about some ideas of how one can analyze and make certain safety guarantees about such learning-based control algorithms. And I just want to illustrate them in terms of this really stylized cartoon example, the RL 101 task of a cart pole that should reach some target destination, preferably without the cart pole falling down. And so now what we would like to do is we would like to plan how to behave by making use of the uncertainty that we get out of the probabilistic model. So here's sort of a cartoon picture. If this is our state space, there's some set of states that we don't want to get at. So typically in the setting, the safety specification comes from some explicit specification of a set of unsafe states, so state action pairs. Now, if you have our agent in some state, we can consider planning forward for some time steps. And since we have uncertainty about the resulting dynamics, there's going to be some uncertainty where we are certain time steps ahead in the future. And now, as long as we use well-calibrated confidence bounds, and we can ensure that these confidence ellipses don't fall into this unsafe subset of the state space, then at least within those time steps, we hope that nothing bad happens. Then, of course, as the agent collects more and more data, the model becomes more and more confident, and hence the uncertainty in the prediction gets smaller and smaller, enabling more and more aggressive behaviors. Okay, so now in order to make this a bit more concrete, one has to first talk about how to even forward propagate these uncertain nonlinear dynamics, and that's generally not an easy task. So we use, if you use, for example, GPs, then the one step ahead predictions, they're Gaussians, right? They're ellipses. But if we iterate them only 2 steps ahead of time, we send these ellipses through nonlinear functions, and they get twisted in a pretty nasty fashion. So one way of dealing with this is to think about conservative over-approximation. And so that's something we looked at in a recent CDC paper to get provably conservative over-approximation of these confidence bounds. But there's also a lot of other ways of how to think about this also in the case of stochastic dynamics, or in the case when one, for example, forward propagates moments of this distribution and so on. Okay, now one challenge is that planning ahead a finite number of time steps may not be sufficient. And here's sort of the picture again in our cartoon example. So while those states are all safe, so the cart pole hasn't fallen at any of those states yet, for those last 2 states here, no feasible control will ever allow us to go back to an upright position, and the cart pole is bound to fall down eventually. Okay, so that means that now we really have to reason about reachability and connectedness, godicity, etc., long-term consequences of those actions. So it's not sufficient to only plan ahead for some finite number of time steps, but we need to reason about long-term behaviors. But fortunately, one can use these confidence bounds even to reason about infinite time and long-term safety properties. And I want to illustrate one way of how to do so using the specific notion of stability as our notion of safety, and using the idea of Lyapunov functions to verify stability of nonlinear dynamical systems. So of course, that's a classic concept from control theory. So here's our state space in a one-dimensional cartoon. Suppose VC0 is a set of states that we have a policy that we can always stay within the states, the set. So it's so-called control invariant set. So for example, this is a set of states we can always stop the car and remain standing. And now what we would do is we would take a Lyapunov function, some positive definite function VS, and look for level sets of this Lyapunov function. So basically subsets of the domain where we are guaranteed with the given policy pi to always go downhill on this Lyapunov function. So if we can ensure this one-step decrease condition, so that this Lyapunov function is guaranteed to decrease for our policy f under our model, for the policy pi under our dynamics f, then we can conclude from this one-step decrease condition, so a one-step property, one can guarantee basically stability for the long-term dynamics. So of course that's a super influential, extremely important idea, and also has been explored quite a bit in the context of reinforcement learning. And now one can use these confidence bounds that I've described in order to verify stability for all plausible dynamics. So if you now have, say, our first principle model and some unknown dynamics, G, that we only have some confidence bounds for, then what one can basically do is to verify the decrease condition with high probability, basically for all plausible dynamics that lie in this confidence interval. Okay, and so then this allows to certify long-term properties like stability, even looking at just these one-step predictive confidence intervals. And now one can put all of those together, for example, in the context of model predictive control. So if you have our region of attraction, so this control invariant set, now we can basically two things. We can basically simultaneously plan a safety trajectory, one that's guaranteed for to always take us back into this safe region, and at the same time, an exploration of performance trajectory that is meant to, for example, collect useful data or optimize stage costs. And now by tying them together at the first action, we can rest assured that no matter what happens in this first step, as long as these confidence intervals are well calibrated, we can follow, in the worst case, the safety trajectory. Otherwise, we can hopefully continue our performance trajectory and learn more and eventually achieve less and less conservative behaviors. And so under those conditions, basically the same regularity conditions that I've described before, one can then actually certify high probability stability guarantees and safety guarantees for this resulting system. Now, one key challenge here is really how to scale to more complex and high dimensional systems and domains. And that is really a very active research topic with lots of really interesting open challenges. I just want to point out one recent result. So it's a paper coming up at NeurIPS this year as well, where we focus on optimistic exploration using confidence bounds. And we show how one can reduce the intractable problem of optimistic exploration and deep reinforcement learning to a much more tractable sort of expected performance objective on a different policy space, so just using standard policy search techniques. So that brings me to the end of the tutorial. I just want to briefly point out some work that's super important, but we didn't get a chance to talk about in more detail. So first of all, there's a lot of really interesting, very recent work looking at learning theoretic results, even for linear systems. So here we focused on nonlinear systems, but there's some really exciting recent work on also linear dynamics, for example, using ideas from regret minimization and many active developments there, and also ideas generalizing beyond sort of Lyapunov stability analysis to more general sort of control barrier functions, and lots of really cool work on safe learning using control barrier functions. So that's basically it. So I tried to give you a little bit of an overview of some important elements that arise when thinking about agents that learn how to act safely in unknown environments. So in the second part, we focused specifically on challenges arising in the context of safe exploration. We talked about the model-free setting with safe Bayesian optimization, but also the model-based setting. And in both cases, the key idea is to use confidence bounds and certainly quantification about the unknown dynamics, unknown reward, safety function, etc., and then basically do robust optimization and formal verification with respect to all plausible dynamics supported by these confidence bounds. And this strategy allows you to then collect more and more data, shrinking these resulting confidence bounds, enabling improved performance going forward. So now where to go from here? So as I said, there's a lot of really exciting questions. So it's a super exciting research area at the intersection of many fields of inquiry: machine learning, controls, formal methods, statistics, decision theory, and so on. Lots of exciting challenges. One crucially important one, of course, is scalability, to really go to high-dimensional state and action spaces, both computationally, but also statistically. So here, you really have to think about uncertainty quantification in these high-dimensional domains, and how to do that carefully given limited data is, of course, a key challenge. Lots of interesting challenges on how to think about interaction in this context. So we saw some ideas in the context of safe annotation learning. There's lots of interesting questions there, but also, say, multi-agent safe learning and so on. Lots of interesting questions. And then on the more theoretical side, questions related to trade-offs between safety and performance, and of course also lower bounds on what can really be safely learned and what can't be safely learned. So with that, I'd like to conclude, and I think we have time to discuss some questions. Thank you very much for listening.
Thank you so much, Andreas, for the wonderful tutorial and giving this really nice overview of all the different flavors of safe reinforcement learning that there are. I'm sure people now have a long list of literature to go through. We already have a couple of questions that I'd like to pose. So the first one is actually related to the very first part of the second part of your talk, and the electron laser example. So here the question is, for the accelerated beam tuning problem, would the policy of don't change any parameters always be safe?
So don't change the parameters would remain safe, but would not necessarily lead to good performance, right? So as I said, the beam fluctuates quite widely depending on environmental conditions, and of course also sometimes has to be changed during experiments and so on.
Okay. And the second question is, so first, thank you for the informative tutorial. And then when you say planning, which method do you rely? Is it nonlinear optimizations of classic AI planning or something else?
Yeah, so a lot of the techniques, especially in the second part, use some form of nonlinear optimization, right? And so there's lots of different techniques that are used in the literature that I won't really give an exhaustive search over, right? But of course, also classical planning techniques are used quite a bit, especially when it comes to sort of formal verification and so on.
Right. So the next question is reinforcement learning dominant in machine learning, or is it only good for specific cases? I guess that's more of a fundamental question where reinforcement learning is placed in the big picture.
I think it's one of the exciting subfields of machine learning. And of course, it's, very closely related, not identical, right, to questions studied in control, right, under different names. So I think it's a super exciting interdisciplinary topic between the different communities, and I think there has to be more exchange also between ideas between the different communities, and there's events happening where these sort of exchanges are taking place. So that's great to see.
Yeah, I very much agree. Okay, while people are thinking about more questions, I actually have one question. So, you mentioned a bit, the dimensionality, especially for, I think, for the electron laser example. And you said that you're doing this by randomly choosing subspaces. And I guess sort of in the limit, you can probably prove things, but practically, does that affect your optimality a lot? Because I would imagine this is a really large scale parameter space that you have to optimize over.
Yeah, so we actually don't choose directions uniformly at random. So we actually use informed sampling directions. So we use informed sampling, posterior sampling. So what you can basically do, so in the paper, we actually discuss various different ways of proposing these low dimensional subspaces. But one thing you can do is you can basically, if you have your Gaussian process objective for that you'd like to optimize, you can linearize the kernel around a given point and now get a distribution over linear approximations. And then one can basically sample from those in a Thompson sampling fashion and optimize with the resulting subspaces. And that often works really well.
Okay, nice. And is sort of the robustness of your optimizer, an issue? When you talk about safety, robustness is often also one, and in the context of Bayesian optimization, is that something that you encountered?
Absolutely. So I think, as I said, this whole question on even how to act reliably on known models has many, many interesting research challenges, right? Solving the resulting minimax optimization problems. Often it's very difficult, and there's a lot of active work on how to address those at scale and so on. It's very complementary to the questions that I focused on here in this tutorial, and I can have a separate tutorial on these types of topics. Right. But that's basically, absolutely. And also there are specific robust formulations, say, of Bayesian optimization that have been explored in the literature. So, for example, so the stable up approach by Bogunovic and co-authors on maximin Bayesian optimization, or the sort of distributionally robust formulations of Bayesian optimization that have been explored by Johannes Kirschner and others in my research group, and so on. So there's lots of interesting robustness challenges that arise algorithmically in a lot of the problems that we're talking about.
Yeah, right. And I guess there's interesting combinations then as well, right?
Yes.
Yeah. Okay, so there's more questions that we should be taking. So first, general question: which direction of RL do you think is more promising, model-based or model-free? That's a tough one.
That's a tough one, of course, in general. And of course, it also doesn't have to be either or, right? And there's also already quite a bit of research lifting ideas from one to the other and so on. So using model-free techniques for solving model-based RL problems and so on. I think, what is most promising? I think it really depends on what kind of applications you do want to tackle. So I think if you really want to make progress on some of the applications that we used at the beginning of this tutorial, just using black box reinforcement learning techniques, I'd be worried about. And so the question is, how can one really think about infusing the right kind of prior knowledge and ensuring certain constraints about the resulting solutions and so on. And I think lots of interesting open research questions along those lines.
Great. So there's a longer question. So it seems like many of the results hinge on well-calibrated uncertainty bounds or quantification. For example, for the uncertainty in the learned dynamics of the model-based RL. Is this a major challenge to applying these results to practical robotic systems? So, and are there any general guidelines for practitioners to solving this in practice, or is it very domain dependent and you need custom solutions basically for each problem task?
Absolutely. So there's a lot more to say about this. It certainly is a difficult problem in practice. So here I focused a bit on the theory, what one can really do. Of course, in practice, there's a lot of research on sort of assessing calibration of different models, but also optimizing the calibration of different models, both in the context of Gaussian process models, but also other models like Bayesian neural network models and so on. So that's a big open research direction, and I don't think there's sort of well-accepted standard principle that is always applied, but sort of a lot of really active work on best practices also.
And then there's one more general question. I'm not sure if I am getting this right. It's so you point out, I think, on this last slide that scalability is one of the open problems. What other open problems do you see sort of on the horizon?
I mean, so I try to mention a few. I mean, scalability alone, you can break it down into many sub problems. So there's algorithmic components, right? How to solve these resulting optimization problems efficiently and so on, or this sort of the question of certification and so on. But then also scalability in terms of data efficiency, and that of course is a huge research topic on its own, right? How to fuse the right kind of prior knowledge. So we, for example, have been looking quite a bit recently into ideas for meta learning, sort of trying to sort of transfer observations from related tasks and learn good priors for say learn good Gaussian process priors based on related tasks that then allow to scale up more in terms of sample efficiency also. And then of course, I mean, inference problems in these models themselves are hard. I mean, it's lots of different aspects of this first bullet alone, right? So I can easily break this down into different slides. So this is certainly one big challenge, but of course also, I mean, many interesting modeling aspects, right? I mean, one thing we haven't really touched at is where do these safety specifications come from, right? That is a notoriously hard problem, right? So, I mean, reward specification and reinforcement learning is a notoriously hard problem, right? And safety specification is similarly difficult, right? Really specifying what kind of behaviors you do and you do not want, and how to encode them. What are general principles of how to do this? How can one do this? Maybe also in interaction, say with a human expert. Lots of interesting challenges. Of course, also questions where you have multiple agents that interact. How do you sort of reason about the uncertainty that comes out of this interaction, right? So sometimes you might want to anticipate certain types of reactions of other agents you're interacting with, say in the context of autonomous driving, for example, and so on, right? And I mean, all of these are big research areas on their own.
Yeah, all of them very exciting topics. So with that, I think we close here. Thank you very much, Andreas, for this wonderful tutorial and overview. We now directly go into the next session without any break, sessions on planning and control. So it fits quite nicely to the topics that we've been discussing here. And our session chair is Aniruddha Majumdar. I'll hand over to you. Thank you.